This is some gold I personally mined in Alaska near Fairbanks. Shiny, metallic, and valuable, there's also something else special about it. Its origin can also be mostly traced to one of the most energetic events in the modern universe. Well, I must admit that this particular gold deposit I mined from isn't special in that regard. In fact, almost all of the planet's gold formed from a series of particularly highly energetic events. Instead of thinking about the particular geologic forces that distribute an elevated quantity of gold to a particular ore deposit in the Earth's crust, we need to think of how that gold formed in the first place, eventually ending up in the Earth. After all, it is common knowledge that the heaviest element a star can create through nuclear fusion is iron, and yet, 54 stable elements higher on the periodic table including gold, and several natural unstable elements still are found in the universe. So, how did these originate? In the case of gold, the answer comes down to three processes. Late lifespan asymptotic giant branch stars, supernovae, and the most energetic of all of these, the collision of two neutron stars. While there are still ongoing debates as to which of these is the biggest contributor in the creation of the universe's gold, many recent estimates indicate that instances where two neutron stars collide create the majority of all gold, possibly up to 92% of all gold that currently exists. Before I continue, I would like to thank this video's sponsor, RadiaCode, which has become a repeat sponsor of my work. RadiaCode is a company which produces affordable yet highly effective smart and portable Geiger counters and spectrometers. These devices not only show you the level of radioactivity an area or object is producing, but also shows you what specific isotopes are creating said radiation. For example, I recently brought my RadiaCode 110 device shown here to the quartzite and Tucson Gem and Mineral shows. At Tucson, the device picked up radioactivity from hard-to-spot tiny splotches of carnotite on select pieces of petrified wood that vendors were selling that they did not know about. Meanwhile, at quartzite, I spotted something even more interesting. I detected a highly radioactive person, which caused my RadiaCode device to register a jump from 15 to 1800 counts per second. The culprit, as you can see here, it was quickly identified as technetium-99m, the main isotope used in nuclear medicine. RadiaCode devices let you visualize the energy lines of incoming gamma rays and explore natural sources, allowing you to see if a work site, house, rock specimen, or ore deposit you happen to be mapping is radioactive, and there is even a mapping feature you can use as part of a free mobile app paired with a device. And now is the perfect time to buy, as if you use this link shown on screen in the top right or in the video description, it will apply an automatic 3% discount to any order you make. Neutron stars, for reference, form when a supermassive star with more than 8 times our Sun's mass undergoes a gravitational collapse followed by a supernova, leaving behind only a tiny collapsed core primarily composed of neutrons squeezed together to an unimaginable extreme. Just not quite enough of an extreme to form a black hole. And this is incredibly dense, with 1 teaspoon of a neutron star weighing 1 billion metric tons. In other words, to get the mass of the Earth in a neutron star, you would only need a sphere with dimensions of 293.7 meters or 963.6 feet wide. Neutron stars tend to have about 1.4 times the mass of our Sun and yet are only approximately 10 to 14 kilometers wide. And when two of these fairly uncommon neutron stars collide, you get a kilonova, a supernova explosion so large that it could render any planets with life on them uninhabitable for a radius of 36 light-years or 340.6 trillion kilometers. While many people think that radioactive decay can only cause one higher numbered element to decay to a lower numbered element, this is not always the case. As, while what I just described is a fairly accurate assessment of alpha decay and beta plus decay, the opposite is true of beta minus radioactive decay. In that process, an unstable nucleus with too many neutrons compared to an ideal state as a whole becomes more stable by decaying into a different isotope, thus changing a neutron into a proton, while also releasing an electron and an antineutrino. And since the number of protons an atom contains determines what element it is, this form of radioactive decay creates a higher numbered element. And do you know what also has an absurdly high number of neutrons compared to other particles? A neutron star, hence the name. Yet, neutron stars in isolation cannot create heavy elements, an immense amount of energy which ejects many neutrons that can only be supplied by one other object is needed, another neutron star. Thus, upon two neutron stars colliding, so much energy is released that hundreds upon hundreds of radioactive decays occur each second in each ejected atom that exists. As neutron stars have a very outermost crust composed of iron, primarily the isotope iron-56. Iron-56 acts as the main seed nuclei for rapid neutron capture to occur, where, as you might have guessed per the name, additional neutrons are rapidly added to a nucleus until it becomes too neutron heavy. At that point, beta- decay occurs, increasing the isotope by one element number. So, iron becomes cobalt, then nickel, then copper, then zinc, etc. When the number of neutrons is reached to completely fill a shell, such as at 50 and 82 neutrons, the neutron capture processes briefly cease and only beta- decay occurs for a time. Since these reactions are occurring more than 100 times per second per atom, the R process, as it is termed, continues until the soup of heavier atoms that are created are actively decaying before another neutron capture can occur. Thus, it takes less than a second for radioactive decay to change a seed nuclei such as iron-56 into gold's only natural stable isotope, gold-197. This very R process was observed in 2017 as scientists watched two neutron stars collide in a distant galaxy 140 million light-years away. This collision created a soup of heavy elements, creating 150 Earth masses worth of gold in seconds. Or, to put this in more familiar terms, this is enough gold to distribute the same abundance of gold that Earth has on 373 billion Earth-sized rocky planets. And yet, despite this abundance, gold is still incredibly rare, as not only are neutron stars rare, but collisions between neutron stars seemingly only occur about once every 100,000 years in the entire Milky Way galaxy out of the 200 billion stars which currently exist in it. However, the R process is not only confined to two neutron stars colliding, it can also occur during core collapse supernova at stars with more than 8 times the mass of our Sun. However, for both causes of the R process, the exact pathway to end up at gold-197 has yet to be identified, hence why my shown diagram stops well short and thus only displays an example R process pathway. However, a third process also exists which can occur during the later stage in the lifespan of so-called asymptotic giant branch stars. These essentially represent low-mass stars with a mass of less than 6 of our suns that have exhausted both the hydrogen and helium in their core. Since yes, our sun is one solar mass, that means it will eventually enter the stage and have the potential to produce gold. Whereas in the rapid neutron capture process, hundreds of reactions occur per second, asymptotic giant branch stars have the slow neutron capture or S process occur within them, where individual decays occur about once every few decades. Neutron captures and beta- decay also occurs with this process, but produced isotopes are generally far more stable than those created in the R process. All of the gold on Earth originated from one of these three processes, with a very small fraction of it through various geological processes ending up in mineable deposits and eventually even jewelry. A special thanks once again to RadiaCode for sponsoring this video, and a special thanks to my patrons and YouTube channel members for supporting my work.